When we divide a number into n equal parts, what matters most to us is the quotient, right? We don't fancy remainders that much and even got exhausted just by thinking that when we divide 14 by 4, there will be a remainder. However, if we are to pay attention to that remainder, we will see patterns. And that pattern is what we call the modular arithmetic, which I, together with my groupmates, will discuss. The concept of modular arithmetic was developed by Carl Friedrich Gauss in his book entitled The Swiss Arithmetic in 1801, when he was only 24 years old. Modular arithmetic, also called clock arithmetic, is the system of arithmetic for integers where numbers wrap around after they reach a certain value, which is called the modulus. Think, for example, of a clock. Instead of having 12 on its spot, let's put 0 and count. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Then we will go back to 12 or also 0. Okay? Which means that 0 is equal to 12 modulo 12. This can also be done in a counterclockwise manner. So, 0, negative 1, negative 2, negative 3, negative 4, negative 5, and so on. Remainders of when an integer is divided by n parts is expressed this way. Z sub n is equal to the set of numbers 0, 1, 2, so on until n minus 1. So if our n is 12, we will have z sub 12 is equal to the set of numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, or if our z is 5, so z sub 5 is equal to the set of numbers 0, 1, 2, 3, 4. Z sub 3 is equal to the set of numbers 0, 1, 2. For you to better understand this, let's have an example. Example number 1. In z sub 6, what is 21? That would be 21 modulo 6 is equal to 3. Yes, because 21 divided by 6 has a remainder of 3. Next, in z sub 11, what is 28? That would be 28 modulo 11 is equals to 7. Why? Because 28 divided by 11 has a remainder of 7. Now that you understood the concept of modular arithmetic, let's hear from Miss Atuel of her thoughts about modulo congruence.
You know that modulo congruence was first introduced by Leonhard Euler in 1750 and developed by Carl Friedrich Gauss in 1801. Modulo congruence is written as and read as A is congruent to B modulo n. Please not be confused of the equal sign used in modular arithmetic. Equal sign is this sign, and congruence are written as this sign. So, A is congruent to B modulo n if A and B have the same remainder when divided by n. For example, 67 is congruent to 32 modulo 5. We can say that this is true because if we divide 67 and 32 by 5, both of them will get 2 as remainder. Whereas 21 is congruent to 19 modulo 3 is false. Because if we divide 21 and 19 by 3, they will get different remainders, which is 0 and 1 respectively.
So there is an easier property that we can use to verify if A is congruent to B modulo n. That is, A is congruent to B modulo n if n divides A minus B. Or, the result of A minus B divided by n is an integer. So for example, let's use the previous examples Miss Cyrene used. So first example, 67 is congruent to 32 modulo 5. So 67 serves as letter A, 32 is B, and 5 is the n. So 67 minus 32 divided by 5. So 67 minus 32 is 35. So 35 divided by 5 is 7. So as we can see, 7 is an integer. Therefore, 67 is congruent to 32 modulo 5. Now let's go to the second example. 21 is congruent to 19 modulo 3. So 21 minus 19 divided by 3 is equal to 2/3. So 2/3 or 0.666667 is not an integer. Therefore, it is false.
Properties of modular arithmetic. If Miss Valio showed you an easy way to verify if the congruence between A and B modulo n is true, I will show you some helpful properties of modular arithmetic. So there are 5 properties of modular arithmetic. So first is reflexivity. Reflexivity, if A is an integer, then A congruent A mod n. Example number 1. 8 is congruent to 8 modulo 11. 8 minus 8 divided by 11 is equals to 0 over 11. So 0 is an integer, therefore it is correct. So example number 2. 1020 is congruent to 1020 modulo 1021. 1020 minus 1020 divided by 1021 is equals to 0 over 1021 is equals to 0. 0 is an integer, therefore it is correct.
So the second property is the symmetry property. And this property states that if A and B are integers, then A is congruent to B modulo n is the same as B is congruent to A modulo n. As you can see, it is just interchanged. A and B are just interchanged. So let's have an example. So 29 is congruent to 13 modulo 4, and the other one is 13 is congruent to 29 modulo 4. So as you can see, 29 and 13 are just interchanged. So let's verify if this is true. 29 minus 13 divided by 4 is equals to 16 divided by 4. And 16 divided by 4 is equals to 4. As you can see, 4 is an integer, right? Therefore, this is true. I mean, the first statement is true. How about the second? So 13 minus 29 divided by 4 is equals to negative 16 divided by 4. So negative 16 divided by 4 is equals to negative 4. And negative 4 is also an integer. Therefore, the second statement is also true. So, it is true. Now, symmetry property is true.
The third one is the transitivity. If A, B, and C are integers, then A is congruent to B modulo n, and B is congruent to C modulo n. Therefore, A is congruent to C modulo n. For example, 36 is congruent to 6 mod 10. 6 is congruent to negative 4 modulo 10. Therefore, 36 is congruent to negative 4 mod 10, where 36 minus 6 is equal to 30 over 10. So 30 divided by 10
from modulo 10 is equal to 3. 6 minus negative 4 is equal to 10 divided by 10, then 1. Then last is 36 minus negative 4 is equal to 40 modulo 10. 40 divided by 10 is equal to 4. So 4, 3, and 1 are all integers. Therefore, it is correct.
The fourth properties is additivity. For integers a, b, c, and d, a is congruent to b modulo n, and c is congruent to d modulo n, then a plus c congruent to b plus d modulo n. For example, a is congruent to 12 modulo 5, and 19 is congruent 14 modulo 5, and then 2 plus 19 congruent to 12 plus 14 modulo 5. So 2 plus 19 is 21, and then C and D is 12 plus 14 is 26. So 21 congruent to 26 modulo 5. So 21 minus 26 is 5, and divided by 5. So negative 1 is an integer, therefore it is correct.
The fifth one is the multiplicativity for integers a, b, c, and d. So a is congruent to b mod n, and c is congruent to d mod n. Therefore, a, c is congruent to b, d mod n. So for example, 2 congruent to 12 mod 5. And we have the CD, which is 19 congruent to 14 mod 5. So 2 times 19 congruent to 12 times 14 mod 5. So we have here the 38 congruent to 168 mod 5. So using the formula, we need to subtract the A and B. So 38 minus 168 over 5 is equal to negative 130 over 5. So we have negative 62. Negative 62 is an integer, therefore it is correct.
So, since we are done with the properties of modular arithmetic, we will proceed to equations involving modular arithmetic. So, example number 1. X minus 3 is equal to 4 mod 2. So, x is equal to 3 plus 4 mod 2. So, we are going to use here the subtraction property of inequality. So, x is equal to 7 since 3 plus 4 is equal to 7, then mod 2. So, x is equal to 1 mod 2 since 7 divided by 2 is 6. So, 7 minus 6 is equal to 1. So, that's why it will become x is equal to 1 mod 2. Okay, example number 2. We have 6x plus 3 is equal to 7 mod 4. So, 6x is equal to 7 minus 3 mod 4. So, we are going to use also here the subtraction property inequalities. Then, 6x is equal to 4 mod 4. The next thing we're gonna do is to find the multiple of 4 that will have the same remainder as we divided 4 by 4. 4 divided by 4 have a remainder of 0, and 12 divided by 4 also have a remainder of 0. So we will use 12. So 4 is equal to 12 mod 4. And 6 is equal to 12 mod 4. And then 12 divided by 6 is equal to 2. So that's why x is equal to 2 mod 4.
So here are the examples of the real-life problems involving modular arithmetic. Example number 1. A man visits his general practitioner every 5 days. If his current visit is Wednesday, what day of the week will the ninth visit be? From the problem, the man already did his first visit, right? Therefore, there are only 8 visits left you have to count. We will multiply that 8 remaining visits to 5 days. So it should be like this. 8 times 5 is equals to 40. Then we will use mode 7 to find the remainder. 40 mode 7 is equals to 5. The answer of the 9th visit is on Monday.
Example number 2. February 29 is on Saturday. On what day will the next February 29 be? February 29 only happens during leap year, right? and leap year only happen every after 4 years. Therefore, next year there will be 365 days, next the same 365 days, next 365 days, and on fourth is 366 days. So we have 365 plus 365 plus 365 plus 366 is equal to 1461. So 1461 mode 7, we will use mode 7 to find the remainder. So it is equals to 5. So the next February 29 is on Thursday.
Modular arithmetic plays a significant role in various aspects of our daily life, often in ways that we may not even realize.
Modular arithmetic is used extensively in timekeeping systems.
It helps us keep track of time, schedule events, and coordinate activities efficiently.
It is also crucial in designing calendars.
It ensures that the days in a week is consistently aligned with each day.
allowing us to plan events, holidays, and schedule.
Algorithms such as hashing functions use modular arithmetic to generate unique identifiers and ensure data integrity.
While these are just a few examples, modular arithmetic has a broader applications in diverse fields.
Its importance lies in its ability to handle cyclic and repetitive patterns.
Maintain consistency and solve problems efficiently.